Swayam Prabha. Digital India. Educated India.
Welcome to the lecture 2, module 4 of concrete technology. We'll start from where we have stopped in the previous lecture. So, in the previous lecture, we are looking at nature of variation of strength of concrete. Now, what we are mentioning, what we mentioned yesterday is that, let us say a concrete we design for a mean strength, or let me call it as an average strength of 55, or let us say 54, somewhere here. What one would find is that large number of specimen or samples would exhibit strength lower than that mean, and again similarly similar numbers of specimens or samples would exhibit strength higher than that. This is so because cube strength of concrete is governed by number of factors. For example, while batching, that is proportioning or weighing the material for putting them into the mixer machine, if I was expected to put in, let us say, 185 liters of water per meter cube of concrete in a given batch, sometime it may be 180, and sometime it may be 190. So, it is very difficult to keep same amount, putting same amount time and again. There is a variation. Similarly, the quantity of cement going into a batch to batch there will be variations, batch to batch there will be variations, and thus water cement ratio would vary, it will never remain constant. And as we have seen earlier, and also we will see later on when we look at the factor affecting strength, we will see that water cement ratio governs the strength. So, if there is a variation of water cement ratio, there will be variation of strength. Similarly, so batching process can introduce strength variation. Similarly, mixing process can introduce variation. For example, you take material from first 15% of the discharge of a mixer machine and make cubes, and similarly you take from last 15% of the discharge of the mixer machine, right, and make concrete cubes, they are unlikely to show same strength. Initial discharge will contain more of the aggregates, later discharge are likely to contain more of the paste. Thus, it is unlikely that both would exhibit same strength or same property. So, mixing also introduces variation. The properties of the material from one batch to another would again vary. For example, aggregate in one batch will not be exactly same as another batch. So, there is variation due to the aggregate properties variation. Variation because of cement properties would vary, and that way one would see that large number of factors would be affecting the concrete cube strength. The cube that is made, the casting of the cube, compaction there, curing condition, they are very unlikely to be identical in all cases. Therefore, strength of the concrete varies. You might have targeted it at some value of 50 or 55, but you might find that it actually varies from somewhere around 41 to about 67. So, there is a variation, and this variation, if I plot the number of specimens in the interval, for example, 50 to 51 here, this is the number of specimens, say about 30. From 46 to 47, you have about 2 numbers of specimen, and similarly here if I look at it 62 to 63, again 2 numbers of specimen exhibited that strength. So, this is the number of specimens showing strength within that interval. 54 to 55 has been shown by majority, and this pattern, if I join by the smooth line, this varies like a bell. This variation is called a normal variation, or concrete cube strength is said to be varying normally or distributed normally. And from the law of statistics, we know that when there is a random variable like cube strength, which is controlled by number of factors such as the proportioning, mixing, properties of the material, etc., under such circumstances, cube strength is likely to be varying in this manner. Distribution of the cube strength is likely to, cube strength is likely to vary in a normally distributed manner, as shown here through the bell curve. All right. The testing process, the casting process, curing, mixing, everything contributes to this variation, and therefore, it is normally distributed according to the central limit theorem of statistics. And such a distribution is a 2-parameter distribution. So, concrete cube, the variation of is concrete cube, population of concrete cube strength is generally normally distributed, that is what we say. And such a distribution is characterized by 2 parameters. One is called the mean, which is the average, arithmetic average of all the data, which you can find out. For example, this strength, one sample, this strength, one sample, class 45 to 46, you have got 2 samples. So, 45.5 will be the representative class value multiplied by the number of samples, and if you sum them up for all the histogram, all samples in the histogram, and find out its arithmetic average, that represents the mean. So, average represents the mean, and in case of normal distribution, the mean, which is central tendency, is also the mode. That is where you find the maximum number of samples showing that particular, maximum number of samples showing strength at this range. So, that is called mode, the peak of this distribution, and also it is the median. That means 50% of the samples should show strength lower than this, and 50% of the samples should exhibit strength higher than this. So, the mean in case of normal distribution is same as the mode and also same as the median, and concrete cube strength therefore behaves normally. So, mean strength corresponds to the mode of the distribution, and it also is the median, which means that 50% of the cube would exhibit strength lower than the mean, and another 50% would exhibit strength higher than the mean. The second parameter through which this distribution is described is the dispersion, how wide this is. For example, if my mixing process do not introduce, or it introduces less variation, batching process introduces less variation, properties of the aggregates from batch to batch vary less, then this range will be smaller, this range will be smaller, this will tend to be smaller, this will get reduced. So, this range of 41 to 67 as seen here could be different depending upon the control that I have. If my batching process is a computer controlled batching process, automated batching process, where all ingredients are weighed within their tolerance limit, my mixing process, the mixer machine is so good that it does not exhibit too much of variation of the concrete from earlier discharge, initial discharge to the final discharge. I have a quality control system where I test every ingredient. Under such circumstances, this dispersion will be less, because as you can understand, the water put in a given batch, it will vary less. I was talking about 185 liters and 180 liters and 190 liters in 1 meter cube of concrete. Now, supposing my batching process is better, and instead of 180 to 190, if the water variation in the water is simply 178 and 182 instead of 182, 185 I said. So, 183 to 187 instead of 180 to 190, then in such case my water cement ratio in the final mix will vary less, hence the strength will vary less. We shall see that strength is governed by water cement ratio when we talk of factors affecting strength. So, if I have better control, this dispersion will be less. So, this dispersion is a measure of control I have. Now, how do I quantify this dispersion? This dispersion is quantified in terms of a parameter called standard deviation SD. So, standard deviation is a measure of dispersion, and as we understand now, better quality control means less standard deviation. Better quality control means less standard deviation, right. So, two parameters, the average, or which represents the mean, the central tendency, and the median and the mode, same thing, and the standard deviation. And we calculate the mean is simply all values of the cube strength, sum it up, divided by number of samples. We can calculate it out, you have possibly would have learned in statistics how to calculate it out when you divide the total range of the samples into various class intervals, take the class representative value and the frequency as we call it, which we have shown earlier, number of samples in the interval, that is the frequency. So, if you know the frequency or relative frequency, the frequency divided by total number of samples. So, relative frequency multiplied by the class values would give in class representative values will give us the mean, or you can have all individual cube strength divided by total number of samples, that will give you the mean. Standard deviation is measured in this manner: deviation of individual samples from the mean, square it up, sum it up and divide by n minus 1 if n is small. But if n is sufficiently large, more than 30, then n minus 1 and n will be nearly same, and this will not be affected. So, S square is called variance, which is the standard deviation square, and square of S is called is the standard deviation usually meant for small number of samples. So, standard deviation square is given as deviation of individual samples from the mean, square it up, sum it up. So, root means square in a way, except that we have taken n minus 1 when it is small samples. Now, if I find out S, standard deviation of population, that we denote by sigma, measure of standard deviation of the population is S. So, S represents the standard deviation of the population. Population means all cube of belonging to the same category. Now, that may not be possible to measure all cubes. So, population actually denotes to infinite sample size, infinite number of samples, not sample size, infinite number of samples, and standard deviation is measured by this formula. So, what we have seen is that standard deviation is the parameter which governs this dispersion, and it has been observed that 99.9% of the data, you can show it by even calculation, because there is a curve that can be fitted to this Gauss's distribution. So, the Gaussian distribution curve is available, equations are available, and if I divide by the even earlier histogram, if I divide by the total number of samples, that we can understand. If I go back to this curve again, if I divide by the total number of samples, this will be fraction, this will be fraction, this will be fraction, all this will be fractions. This is called relative frequency, and sum of all these fractions will be equals to 1, because sum total of this number of samples here, number of samples here, number of samples here, number of samples here, all this is a sum total of all those number of samples is a total number of samples that is equals to n. So, total number of samples. So, sigma Fi is, f is the frequency, is equals to n, and relative frequency is given by Fi by n. So, Fi is this one. If I call this as f1, f2, f3, etc., etc. So, Fi, any ith one, so this is Fi. Sum total of Fi divided by n is equals to 1, because sum total of Fi divided by n, because sum total of Fi is equals to n. So, this is equals to 1. So, if I sum up all these fractions, I get 1. So, area under this curve is therefore can be approximated as 1. So, total area under this curve is 1, total area under this curve is 1, and since it is symmetrical, this area must be 50%, 0.5. This area must be 50% of the total area, and this area must be 50% of the total area. And it has been observed from the equations, one can show that this 99% of this area is contained within plus 3 standard deviation and minus 3 standard deviation. So, if I go 3 standard deviation, because total dispersion, standard deviation is a measure of the dispersion. So, everything is contained within plus 3 standard deviation and minus 3 standard deviation, all right. And if I go 1 standard deviation away, that is 34.1% of the area is contained here, another 13.6% of the area is contained here, another 2.2% area is contained here. Similarly, 34.1% area is contained within this 1s, and within this 2s and 1s 13.6. Since it is symmetrical, same thing is valid. Now, as far as concrete grades is defined, we define characteristic strength. If you remember, we defined characteristic strength. How did I define characteristic strength? Characteristic strength is that strength which is exceeded is the strength exceeded by 95% of sample. Strength that is exceeded by 95% of the sample, strength that is exceeded by, just let me write it. So, FCK, we denote it by FCK, is strength more than 95% or more, 95% or more, 95% or more sample, or samples, or more samples would exhibit strength greater than equals to FCK. So, that is how we define. Now, mean strength, if I call it Fm as the mean strength, if I call Fm as the mean strength, Fm as the mean strength, if I call Fm as the mean strength, 50% of the sample will exhibit strength more than Fm. So 50% of the samples will exhibit, so 50% of the samples would exhibit strength greater than equals to Fm, because we said mean and median is same, and at median 50% of the strength samples should show strength more than the median and 50% shows below by definition. So therefore mean median coincides, therefore 50% of the samples should exhibit strength more than mean. So if I now go to this curve, this strength will be 50% of the sample will exhibit strength more than this, 34 plus 13.6, 2.4, 34.1, 13.6, 2.2, if you see 9, and this is 49.9%, and would show more strength more than that, right? And 49.9% or 50% will show strength less than this. Now I want a strength that would be exceeded by 95% of the sample. So it will be somewhere this side, it would be somewhere on this side, it would be somewhere here, it would be somewhere here. So my FCK is here. 50% of the sample, 95% of the sample would be showing. For example, you come here, 50 plus 84.1% of the samples would show strength more than this. So for 95, it would be somewhere here. 5% of the area would be here, and 95% of the area would be on this side. So this is what is FCK, and corresponding to this, we know that this, for example, at 1s distance, 84.1% of the sample would exhibit strength more than mean minus 1s. So Fm minus 1 standard deviation, this strength would be exhibited, 84.1% of samples would exhibit strength would exhibit strength greater than this. 95% of the samples would show strength. This is related to 1 sigma. So Fm minus 1.65 sigma, because from statistics we know the 95% of the area corresponds to 1.65 sigma, 1.65 sigma here. Therefore 95% of the area is on this side, therefore FCK is somewhere here. So FCK will be equals to Fm minus 1.65 sigma. FCK is equals to Fm minus 1.65 sigma. Thus Fm is equals to FCK plus 1.65 sigma. This is an important aspect. So therefore you can see, if my standard deviation is higher, then target mean strength will be high for the same strength, same FCK, standard deviation is higher, mean strength for the same strength grade or FCK, mean strength will be higher if standard deviation is higher, right? This is an important issue. We shall discuss this sometime later on when we talk of quality control, right? So mean strength is related to grade strength in this manner. Now while testing or making trial mixes, I can verify this. It's very difficult to verify this. To verify this, I got to test large number of samples, which is almost impossible to do. So we test small number of samples and get an estimate of Fm, which we call as target mean strength. So we do mixed design for Fm, because it is possible to get an estimate of FM from testing small number of samples, let us say 3 samples or 3 cubes, 3 specimens making a sample, or number of samples if I test, small number of samples if I test, I can get a measure of FM. But it would be difficult to get FCK directly. So, we design the concrete mix for target mean strength, that is FM. All right. This will be clear when we talk something about quality control later on. So, we design the concrete for target mean strength, that is mean strength, because in the laboratory I can get an estimate of mean strength easily by testing smaller number of samples. If I want to get FCK, I require lot more cubes to be tested, and from a large number of data, then I have to establish this curve and obtain this. So, first step in all mixed design procedure is to come with a mean strength. So, mixed design procedure first step would be to get a mean strength. Mean strength. Characteristics grade strength, quality control, that is your sigma, FCK, and this gives me mean strength. That is the first step. So, we can look in the procedure of mixed design. First step is to get the mean strength. Then strength is governed by water cement ratio. This is an empirical observation. First by D. A. Abraham, some time during 1920s, and this is still valid. We consider it, this is acceptable at all level, although there are other kind of approaches available, but generally strength versus water cement ratio relationship has been accepted, and it is understood that strength is largely governed by water cement ratio. So, in mixed design procedure, we have now got the strength, therefore, we can determine the water cement ratio. From the strength we can determine the water cement ratio, because water cement ratio governs this strength. But when all other things remaining constant. So, this all other thing involves type of cement based on the chemical type of cement and age at which the strength is required. These are other factor. So, age, strength and age both decides water cement ratio. But we have also mentioned earlier in the previous lecture that durability of concrete also controlled through prescription of water cement ratio, depending upon type of cement, Now, for example, if you have an application or a site where sulphate attack, there is a possibility of sulphate attack, you might use a slag cement or sulphate resisting cement, where you expect mass concreting to be done, heat of hydration may be a problem, you might use low heat cement. So, if you use, let us say, sulphate resisting cement, the water cement ratio for sulphate resisting cement from durability point of view might be given or must be prescribed in the code. So, the water cement ratio prescribed in the code for durability for given type of cement, which you choose depending upon the liability of chemical attack or mass size of the concrete mass. For example, if, as I said, if it is a marine environment, possibly you will prefer a slag cement. An environment where sulphate attack is prominent, maybe sulphate resisting cement together with slag cement. Of course, if sulphate and chloride both are there, sulphate resisting cement is not good. So, once to, depending upon the kind of chemical attack you are likely to have, you will choose the type of cement. Also, mass concrete you select low heat cement. If you want quick strength, then you might select rapid hardening RHPC, Portland cement, rapid hardening cement. Portland pozzolana cement for low heat of for mass concrete, and also for better durability, for example, alkali aggregate reaction, etc., etc. You might also select low alkali cement if it is alkali aggregate reaction. So, type of cement depends upon liability of chemical attack and size of concrete masses. Now, water cement ratio is also prescribed from durability and from strength required at a given age, you find out the water cement ratio. For these two conditions together, durability, type of cement that is used for durability, and water cement ratio is prescribed for the given exposure condition, you find out the water cement ratio. Finally, select the water cement ratio. The selected from least of the two. First, you see what is the water cement ratio required for strength, also the water cement ratio required for the type of cement for durability purpose. Whichever is lower, you select that water cement ratio. So, first step in mix design is to find the mean strength. Second step would be to find out the water cement ratio. This is a conventional mix design. Most of the mix design method follows this method. Second step would be to find out the water cement ratio. First is the mean strength, water cement ratio from the mean strength and durability concerns for the given type of cement and age at which the strength is required. Right. Then followed from this water cement ratio being known, second step. Third step would be to determine the water content or paste content. You see, method of compaction, size of the section and spacing of reinforcement. See, method of compaction decides workability, size and spacing of the reinforcement also defines workability. That is what I said, which is specified normally. So, required workability is specified from method of compaction, the section itself and spacing of reinforcement. And then this workability is controlled by maximum size of aggregate and aggregate shape, not really texture much, but shape, mostly the shape. Remember, when we discussed about aggregate, we said that maximum size of aggregate improves the packing density. Rounded aggregate or aggregate shapes improves the packing density, and therefore, the amount of workability or the mobility, moldability required for concrete, which is a function of the paste content. So, the paste content would govern the workability, that is what we mentioned in the previous class. So, from the required workability, type of aggregate, maximum size of aggregate and aggregate shape, etc., etc., including grading of aggregate, we can determine the paste content. So, overall grading and packing of aggregates, we can determine the paste content and also either the paste content or the water content of the mix, because water cement ratio being fixed, if I choose water, amount of water, if I fix the amount of water, cement content will get automatically fixed. So, most of the mix design method, what do they do? Based on the workability requirement, maximum size of aggregate, shape of the aggregate and overall grading determines the water content, which essentially ensures a required paste content. If I know the paste content, if I know the water content, then obviously I can find out the cement content, and if I know the cement content and water content in all the contents, cement content, water content, these are all expressed in terms of mass per unit meter cube of concrete. So, in unit volume of concrete, how much of water, how much of cement I need, that I can find out. First, I find out the mean strength. Corresponding to the mean strength, I find out the water cement ratio and also look at the durability part of it. Whichever controls the water cement ratio, from that I fix the water cement ratio. Then if I can fix the water content, I have got the cement content also. The water content is fixed from water content per meter cube of concrete is fixed from workability, maximum size of aggregate, shape of the aggregate and overall grading. In fact, that governs the paste content required, because the packing would be dependent upon the grading proportion of the sizes, relative proportion of the sizes, and also shape and maximum size of aggregate. So, this will depend the packing, and depending on the packing characteristics or packing density of the aggregate, the paste content required for a given workability would be, paste content required would, will govern the workability. So, if I know the workability, I can actually find out paste content, but many mixed design method, what it does, they fix the water content, because automatically water cement ratio being known, paste content will be controlled. So, therefore, once the paste content is known, or in other words water content, cement content is known in kg per meter cube, rest of, if I know the total density of the material, then I can find out wet density of the material, I can find out the aggregate content. Or if I know the total volume is 1 meter cube, if I know volume of these two component, rest of the volume is the aggregate content. So, total aggregate content, therefore, simultaneously I can find out, and if I know proportion of each size fraction aggregate content, then I can find out mixed proportion, that is every size fraction I should be knowing. So, water cement ratio has come from earlier, paste content and aggregate content being known, proportion of each size being known, I can find out the mixed proportion. Then I use this, knowing the capacity of the mixture, I find out weights of ingredients per batch. So, this is the overall mixed proportioning process or mixed design process, as conventionally it is called, but actually it is, truly speaking, it is actually mixed proportioning, that is all we are doing. Design is conventionally used, perhaps it is more appropriate to call it mixed proportioning process. So, this is the overall mixed proportioning process. To look at it again, first determine the water cement ratio from chart or table. This will be from Indian code, of course, but let me just see. Overall process looks like this, and total aggregate content is determine the water cement ratio. So, if we look at overall process, we determine water cement ratio from chart, table or experience, depending upon the method. Water cement ratio and water content being known, cement content can be calculated. Total aggregate content is then calculated assuming conservation of volume, and fine content is calculated from coarse to fine ratio. Let me look at it again. First is the target mean strength. They then determine water cement ratio dependent upon the strength from chart, table or experience, and use durability criteria also. Next step would be water cement ratio known, many times you determine the water content from some other table, C can be calculated, and then total aggregate content is calculated, because W and C is known, rest of the material I can find out, that is the aggregate content. Volumetrically, volume proportion of aggregate can be calculated. If I assume that sum total of all volume will be 1 meter cube. So, that is conservation of volume, and fine content is calculated from coarse to fine ratio, which dictates my packing. So, that is the procedure. Just to repeat it again, you see, this is my water, this is cement, it could be fly ash or some other cementitious or filler material, or some other supplementary material or mineral admixtures, whatever you call it, this fine aggregate and coarse aggregate. The strength is a function of water cement or water to cement plus fly ash, maybe so with some factor. So, effective fly ash or effective equivalent cement for fly ash or any other material, cementitious material. So, water to cementitious material ratio, equivalent cement content, equivalent water cement ratio. Workability is a function of water content, plasticizer if you are using any, aggregate packing characteristics, and also the filler or fly ash content. So, if I know this, I can find out the paste content. This is the basic idea. Then durability is also function of water to cement ratio and curing, etc., and cement content. So, based on this concept, first we find out this, then we find out this in many cases. Of course, this we do, first we make a control mix, then we modify this mix with this one. And finalize the water cement ratio based on these two criteria, and then usually total volume is conserved, and therefore sum total of all materials must be equals to 1 meter cube. So, if I have found out cement, fly ash, and this is equals to 1 meter cube. So, if I have found out cement, water and fly ash, this volume I can find out, and if I know the proportion of these masses and their specific gravities, so this one too also I can find out. So, that is the overall mix proportioning or mix design process. Right. Now, having gone through the general process of mix design, that is used by most of the methods that is used, we can now go to specific method like Indian method. Obviously, in all cases you have to make trial batches and you have to re-optimize this. Although specific property like strength, slump, etc. should be measured for a batch and verify that you have got it, and you have not got it, then redo the trial. So, finally, the thing is that it is final adjustment would be needed, and then you find out the correct content per unit volume for economic evaluation. How much quantity you require for 1 meter cube of concrete, final 1 meter cube of concrete. Therefore, that goes for calculating the cost, etc., etc. Now, since we said that it is empirical and there is some amount of art involved, hence there is no unique method. We have seen a general procedure that is adopted by most of the method, but it is all empirical. We can see that actually strength, first we find out from the grade strength and the standard deviation, find out the target mean strength. Up to this there is no problem, but after that we find out the water cement ratio from tables, charts, etc., etc., or from experience, right. And finally, of course, you have to do the trial mix. So, the method is purely trial and error, laboratory based and empirical in nature. Then you find out the water content again from tables and charts, etc., and then only you use the concept of conservation of volume to find out the total aggregate content in some manner. We shall see that actually here the different method differs a little bit, and if you know the fine to coarse proportion for the packing characteristics or the grading requirement, then you can find out the fine and the coarse aggregate component of the mix also. So, it is purely empirical, hence no unique method, no unique method. Method to method differs, and therefore, you have got Indian standard method IS 10262, yesterday I mentioned, last lecture I mentioned, current one is 2009, and then this we will discuss also about British DOE method. UK is not there in the code, but Department of Environments, this Department of Environment method, then SCI method, and some modern concepts, that is what we will discuss. So, to start with, we will start with the IS method today and follow up with the other method, right. We will do an example in the next class, but let us see IS method now. First step is find out the mean strength, and this is the formula. So, if you have 25 grade of concrete is M25, so it will be 25 plus 1.65 into standard deviation. The standard deviation would not be known to one in the beginning, but once somebody you have done some trial casting, then standard deviation will be known. So, the code says the standard deviations, it gives you some guidelines to start with. From 20 to 25 grade of concrete, M20 to 25, you use 4 MPa as sigma equals to 4 MPa. For 30 to 50, you can assume it to be 5 MPa to start with, but determine this from site data as soon as 30 samples are available to you. because it could be less or it could be more, it could be more or less, this could be more or less, and in such case your mixed design proportion that you are giving is not correct, because it will not give you the right strength. So, determine it as soon as possible from 30 samples. So, that is the first, but however, you calculate out Fm. Then it says you determine step 2, determine the water cement ratio, selection of water cement ratio from experience or established relationship. Now, if you have already done a lot of mixed proportioning, with the same aggregate, same sand, same cement and same kind of material altogether, then possibly from your experience you can choose, okay, it is M20 grade of concrete, I need a water cement ratio of 0.55. Well, M50, possibly I need water cement ratio of 0.35 and so on. So, from experience it can come. If you have nothing, no experience, then go to the IS 456-2000 durability prescription, which gives you water cement ratio for various exposure condition. Anyway you cannot violate that. You cannot violate that. For example, if the maximum water cement ratio prescribed for your exposure condition is 0.45 and from strength you find out to be 0.48, you will be always using 0.45. So, your starting trial can be durability criteria. Durability criteria, we will discuss this when we talk of durability of concrete sometime later on. So, durability criteria, this is given in the IS 456-2000 table 5, I think. So, from that you can choose the water cement ratio if it is, you do not have any experience, first time you are using the material and things like that. So, first trial you can use that water cement ratio. So, it has become actually a simple thing, not complicated, because in any case you can't have water cement ratio more than the durability requirement, you can have something less. Step 3, it gives you a table from where you can estimate the water content. This table is meant for angular coarse aggregate and slump 25 to 50 millimeter. For other cases you apply correction factors. So, you have got maximum size of aggregate 10 millimeter, then your water required is 208. If maximum size is 40, water required is 165 for angular coarse aggregate and slump 20 to 50 millimeter. Now, this one can understand, as my aggregate size MSA increases, my packing improves. So, I will require less paste, therefore, less water. Water reduces because with larger MSA I will require lesser paste. That is what we have understood when we talked of aggregate, in the previous module, previous module. So, packing characteristics improves if I increase one more size, and therefore, here compared to this I have increased 2 more sizes. So, water content required is less. So, water in kg per meter cube for MSA 20. So, this is the first starting table, but this is meant for angular aggregate and slump 25 to 50 millimeter. But if I have then rounded aggregate and different slump, then I use a correction factor. The correction factor is same step continued. I am trying to determine still the water content. For each additional slump of delta 50 plus additional. So, this was 25 to 50. If it is 50 to 70, 100, then I would increase the water content by 3%. So, if you require more slump, you have to increase the water content, because paste content you have to increase, and workability is a function of paste content or water content as such also will give you better flow. Now, if you have, that was for crushed aggregate, that was for, if you look at it, that was for angular coarse aggregate, they did not say crushed, in our code it is angular. Now, if you have better shape, for example, subangular, then you reduce the water by 10, because subangular packs better than angular, and if it is rounded, you can reduce it by 25. So, whatever water you have got, first this correction, if you have higher slump, add 3% for each 50 mm increase in slump, and reduce the water content depending upon the shape of your aggregate. If it is gravel and crust mixed together, then -20, subangular -10, completely rounded aggregate -25. If you are adding a plasticizer, you can reduce down this water by 5 to 10%, and if you are adding a super plasticizer, you can reduce it by 10 to 30%. And in the last module, we talked of plasticizers and super plasticizer. We have discussed that super plasticizer can reduce the water up to about 30%, while your dosage is also high in case of super plasticizer, and plasticizer dosage are less, right? Up to 2 possibly 0.6 to 2% is for super plasticizer, and plasticizer doses are less, and it reduces only about up to 12%. We said IS code allows you to reduce the water by 5 to 10%. So the water content you can reduce in this manner or increase. So therefore, corrected water content you are able to find it out. That is step 3. Step 4, estimation of coarse aggregate volume per from a table, and this is the table looks like this. Depending upon the sand, which we said was, when we were talking of aggregate, we talked of zone 1, zone 2, zone 3, zone 4 sand, which is very fine, this is coarse. So depending upon the size fraction of the sand or size of the sand, in Indian code IS 383 classifies the sand depending upon their particle size distribution. Coarser sand is zone 1 sand, zone 2 sand is less coarse, zone 4 is very, very fine compared to zone 1. So depending upon that, the coarse aggregate content would per unit volume would depend upon that, because packing characteristics would change. For example, this is fine sand, so therefore coarse aggregate volume would 50% of the volume of the total aggregate will be coarse aggregate, rest 50% is a fine. Whereas here it is 44%, because you will have a better grading, and within this the 44% is here, and it will also depend upon MSA. Higher the MSA, you can use larger proportion of volume proportion of aggregate, volume proportion of aggregate. They will have less void in the system. They will have less void in the system. In this they will have less void in the system, and in this you use more coarse aggregate, because fine aggregate there some materials are missing. So some materials, some of the larger size will be missing. So that's filled in by fine aggregate, the zone sand itself. So this direction it increases, because you can use more amount of coarse aggregate, because they will have less voids. Same if you keep the same voids, if you keep the same voids, this will have, you use 75%, it will have lesser voids in them for the given sand, and as the sand becomes coarser or coarser, this required coarse aggregate volume reduces. So using this table, you can find out the coarse aggregate volume per unit volume of total aggregate. So now with all this information known, one more additional factor is that if you are using the concrete for pumpability, you should reduce the coarse aggregate by 10%, because coarse aggregates are not pumpable. So if you want to improve the pumpability, you must reduce down your aggregate content, coarse aggregate particularly, and coarse aggregate should be reduced. You should have more mortar to make it what is called saturated in pumping situation. Make it more mortar, and mortar should have adequate amount of paste or more paste in pumpable concrete. So 10% aggregate is reduced in case of pumpable concrete. In another concrete which is self compacting, doesn't require vibration, aggregate content, coarse aggregate content is even lesser. So in pumpable concrete, actually more paste should be flowable, and is a paste which flows. So if you put sand, mortar itself will be flowable. Aggregates are not really pumpable as such, so that should be less, and they should be embedded in the mortar system, right, rather than just mortar filling up the voids in the aggregate system and slightly more. Now aggregate should be embedded in the mortar system, and that's why you have more less aggregate, coarse aggregate content in pumpable concrete. So what we have got so far? We have determined water cement ratio, we have determined water content, corrected it accordingly to with my slump, type of aggregate, MSA, etc., etc. So, I have got water content, target mean strength, water cement ratio, water content. Therefore, I need know also the cement content, because water cement ratio is known, and then I know the volume fraction of the total aggregate in the overall aggregate system, volume system of coarse aggregate in total aggregate system. So, once this is known, first thing I do is I find out the cement content, which will be the maximum of water by water cement ratio. This is known to me now, and this is also known to me, water cement ratio, and C specified for durability in the code. So, IS 456 2000 in its table, it gives you it gives you C for durability, whichever is greater, either you find out by W divided by W by C star, where W C star is the one which you are using, this will give you cement content, or C for durability, whichever is greater you use that. Water cement ratio, of course, you find out as water cement ratio star is equals to minimum of W by C strength, comma W by C durability, whichever is lower you use that, whichever is lower you use that. So, W by C strength that you find out from table, and W by C durability that you have found out from, either used, found out, or maybe if you are using a starting criteria, it will be from there. Then using this formula, that is volume water divided by 1000, because specific gravity of water is 1000 kg per meter cube. So, water content divided by 1000, cement content divided by specific gravity of cement divided by 1000, that is the volume of cement in 1 meter cube, volume of water in 1 meter cube. This is the volume of coarse aggregate in 1 meter cube, and volume of coarse aggregate in 1 meter cube, right, divided by 1000 anyway. Now, this volume can be calculated, volume of fine aggregate can be calculated, because we know the volume fraction of coarse aggregate from the previous table. So, 1 minus that will give you the volume content of fine aggregate, and total, because the total this volume, this sum total of this volume and each individual volume can be calculated, because volume of coarse fine aggregate is equals to 1 minus volume of coarse aggregate, because we have found out the fraction from the previous table. From this table we have found out, from this table we have found out the proportion of coarse aggregate in the total aggregate volume. So, volume of fine aggregate we can find out, and once sum total of all this volume must be equals to 1. There is no air content in this code now. So, no any one of them is known, one unknown I can find out, because both can be converted in terms of 1 minus B CAG is equals to B FAG. Therefore, this can be written in terms of this, and I can find out the total volume, total proportion of all, because this is known, this can be calculated out. If this can be written in terms of this can be written in terms of this, and I can calculate out this one. So, all proportions are known to me, and with all proportions known to me, I can actually now get the complete mixed proportion. Actual water to be added at the site will be the water that I have calculated minus the water that is present in the aggregate. Now, present minus absorption, because SSD condition I am considering. So, what is required for SSD condition, that I must subtract. So, some correction is needed at the site, because there will be some moisture present in the aggregate, and accordingly I must do correction such that it is in SSD condition. Similarly, actual quantity of aggregate in the mix shall be aggregate content plus the additional required, because there will be some moisture in the aggregate. So, this will be clear when we look into the next example, and then trial mix 2 after adjustment of slump, maybe trial mix 3 and 4 with same water, but water cement ratio plus minus 10%, and final adjustment. So, for fly ash you can increase the overall cementitious material by 1.1 C, and C and F dash can be calculated. Well, this is, so with this we just complete this. Next class we will start from the same one, same last end of this particular lecture, And we have discussed about so far general process, we mentioned the methods, and we have also discussed about IS method. So, from the correction of IS method we will start and go through an example which will make IS method completely clear, and then in the next lecture first we will go through an example, discuss about DOE method. Thank you very much for your hearing.